We started discussing ray optics on Tuesday in the previous lecture. Let me just quickly review what we've discussed. So first of all, we switched from wave optics to ray optics. Ray optics can be applied if wavelength of light is much smaller than the size of the object with which that light interact. In that case, there is no point of messing up with ray optics. It's much easier to use a different model, ray optics. So then we introduced rays, right, which we can use to discuss optical phenomena, to represent light. So direction, rays, just basically straight lines with a direction. They are perpendicular to wavefronts, right? And of course, they point in the direction of light propagation, right? Okay, so we introduced arrays. Then we introduced objects to this world of ray optics. So there are two types of objects. Some of them are active or self-luminous, basically sources of light, right? Objects which can generate light. And objects, passive objects, or reflective objects, which don't generate lights, right? So we see them just because they reflect light produced by some self-luminous object, some active object, right? So active, passive. Then next, of course, light propagates in media, right? Oh, in different media. All right, so we discussed all possible interactions of light, which is represented by rays, and medium, right? And here we put two media next to each other to have a border, because very often we have borders between media in optics. So, and as a result, we introduced four types of interactions. So first, reflection at the border, at the interface between two media. Then, reflection. Then, refraction, when light manages to get into the second medium. Then, scattering and absorption. So as I said at the end of the previous lecture, so in this course we're going to discuss only reflection and refraction. Scattering and absorption you are going to discuss in the higher level classes, right? Okay, so let's pretty much that's where we finished in the previous lecture, and now let's discuss first reflection and then refraction, and then at the end I'm going to look at one problem. So reflection. There are two types of reflections, and examples of those reflections are these. Okay, I have a mirror, right? So one type of a reflection, and I have just a piece of a cardboard. The second type. In the mirror, of course, I can see myself. Here in the cardboard, I cannot see myself at all, right? So. Two examples of these two reflections. I just hit my eye. All right. First one, a reflection from the mirror. It's a reflection from a smooth surface, right? So let's assume that this is the surface of this surface of the mirror, all right? Smooth. And so let's look at let's draw one ray, right? So this ray which hits the surface, right, or incident on the surface, we call as an incident ray, right? Of course, this ray will be reflected, and of course, this ray we call as a reflected ray. Then, of course, you can draw more than one ray, okay, incident ray, and of course, more than one reflected ray, right? So you can draw something like this. Now, how can we define a direction of this ray, incident ray, and direction of reflected ray, because we need that. We need that to discuss image formation later, right? To discuss light propagation and so on. So we need to define a direction of, let's start with an incident ray. So let's draw a line normal to this surface, to the surface of the mirror, right? So normal, perpendicular. So, and now basically, it's more or less obvious that you have two choices. Obviously, it's better to use an angle. Which angle? You can use either this angle, you see, between the surface of our mirror and the ray, or between the normal line and the ray, that angle. Which one is better? It's difficult to tell. They're equally good. So pretty much at this point, it's a question of convention. Which angle people decided, okay, researchers, right? The researchers decided to use. So researchers decided to use the angle between the ray, okay, between this ray, and the normal line. So this angle, right? So basically by convention. So remember that, because on the exam, some students use wrong angle, right? So this angle is called the angle of incidence, angle of incidence, because it gives the direction of an incident ray. Then, of course, in a similar way, we can define a direction of the reflected ray using the same angle between the normal line and the direction of the ray. So this, of course, we can call as an angle of reflection. Right? So theta sub I stands for incident, angle of incidence, and theta sub R stands for reflection, right? So theta sub R, angle of reflection. Now it's time to state law of reflection, right? Law of reflection. I will say a few words in a few minutes about the word law. But anyway, let's state this law. And it consists of two parts. First part, here we have, okay, during the reflection, process of reflection, we have basically three directions. Incident ray, normal line, and reflected ray. And according to this law of reflection, directions, okay, this is incident ray, this is normal line, and this is a reflected ray. So directions, okay, of all these, it's difficult to hold it, okay, like this. So all these three directions must lie in the same plane. It's impossible to have situation like this, no way. So all the time, these three directions must lie in the same plane. The reason, I will explain in a second. Right. So it's the first part. Right. So, and the second part, everyone in the world knows angle of incidence equals to the angle of reflection, right? So theta I equals to theta R, right? So these two statements are called law of reflection. Okay, now, as I promised, a few words about the word law. You remember what law is usually? It's something fundamental, which cannot be derived, like a Gauss's law, Ampere's law, Faraday's law. All right, so those are laws. They are written usually based on observations, and we treat them basically as axioms, right? Which doesn't require derivation, because it cannot be done. But this law of reflection can be not easily, but can be derived. You just grab Maxwell's equations, get from them wave equations, and then apply boundary condition in this situation. And this will appear naturally. So boundary condition, there will be light, wave equation describing light in this medium, then light describing, wave equation describing light in this medium, and again you apply boundary condition, and both of these statements appear naturally. You just do math, okay, calculus, and you will get them. So since it can be derived, so strictly speaking, we should not be call it law, but nevertheless, it's a widely accepted sort of name, law of reflection, and of course we are going to use it also. All right, so the second type of reflection, reflection from a rough surface. Yeah, also this very often is called the specular reflection, right? And example, you see reflection from a surface of water. Image formation we will discuss on the next slide, right? So why do we see this image of the boat in the water, right? So then, second, reflection from a rough surface. So you see lots of roughness. And again, like in this case, let's send a bunch of parallel rays. Let's assume that bunch of parallel rays are hitting this surface, right? But now you see these rays are going to be in different conditions, right? So, for example, if you take this ray, it is going to hit the surface at this particular point where this ray hit the surface may be flat, maybe horizontal, right? And then, of course, you apply a law of reflection, and you can get a direction of the reflected ray. Then, if you take, for example, this ray, at that particular point where this ray hits the surface might be at a position like this, right? That surface at that particular point. So, according to the law of reflection, this ray will be reflected that way. Then, similar. Okay, this ray maybe hits the surface, and surface at that particular point is in this direction, or oriented like this. So according, again, law of reflection, this ray will be reflected this way. So pretty much this that way, this ray will be reflected this way. So you see pretty much all these rays will be reflected in all possible directions, right? So if, for example, these incident rays carry some information, for example, about me, let's say image of me, all right? But after reflection from this rough surface, all this information will be just spread all over the place, right? So you will never be able to see anything. So that's why when you look at the surface, rough surface, you cannot see anything, right? Because basically information is scattered completely in all possible directions. Right? So most of surfaces, of course, in our life, they are rough surfaces, and of course, light experiences what is called a diffuse reflection. Even when we read a book, right, for example, of course, the surface of a paper is still an example of a rough surface. Okay, so most of the time we're going to deal with specular reflection in the problems, although it's almost the end of the semester, right? So we're not going to look at that much, right? Because it's easier to describe. This is more complicated to describe. So now let's discuss an image formation. Like over here, you see the image of a boat. So how come that we see that in the case of a specular reflection? So now let's discuss that. So as I said, image formation in a mirror, for example, right, on a smooth surface. So let's assume that we have, for simplicity, let's start with the simplest possible situation, that here's the object, and let's assume it is an active object, basically like maybe a bulb, right? Which, of course, generate lights, and of course that light will be sent in all possible directions. And then, since we want to discuss image formation in a mirror, okay, so let's pick a mirror. So this is our mirror. Then, since we want to discuss image formation, image is formed, in order to see an image, you need to have a detector, right? Without putting a detector in this picture, there's nothing to discuss. So detector is our eye. Yeah, in scientific terms, our eye is just a detector of visible light, right? visible light. All right, so let's assume that this object is at the distance s from the mirror, and of course the eye. All right, so this is the length of our eye, and so now let's discuss. So what are we going to see here on our retina? Okay, so let's start with an object, which we assume is an active object, and of course it generates light, and that light goes in all possible directions. So of course we can draw as many rays as you want. I drew here 6 rays, right? And they all go in different directions. But most of the time, when you discuss image formation, you just need to discuss just a few rays. Usually 2 or 3 rays are enough to discuss an image formation. So let's pick the first one, first ray. Let me pick this ray, which hits the surface. Of course, then according to the law of reflection, will go, and let's assume that this ray will hit the center of our lens, right, lens of an eye. And of course, it will end up on the retina, giving us some information about this source, about this object. But let's add 2 more rays. So the second one, which I want to add, is going to pass this lens at the top of the lens, right? So let's pick a ray. Let's say it hits the mirror at this point, and of course it will end up here at the top of the lens. And of course that will be basically the last ray, okay, on this side, right? The last ray, which is going to end up on our retina, right, giving us some information about the object. If I take this ray, you see black, after reflection, it's not going to hit our lens, and of course it is not going to contribute anything to the image formation in our eye. All right? So, and now let me add one more ray, which is going to hit the lens here at the bottom. So let's assume that it's this ray. So after reflection, it hits this side, the bottom of the lens, and ends on our retina. So pretty much only these rays, right, between these and these, are going to contribute to the image formation in our eye. So if I take a ray, for example, this one, which hits the mirror over here, it is going to miss our lens. So now, after this, now it's a work of what? Of our brain. Okay, collaboration of our brain and the eye. So now our brain starts interpreting. So to our brain, it looks like this ray. Let's take the central ray. So for our brain, it looks like that this ray came from a source which lies. Okay, actually, let's take this ray. So for our brain, it looks like this ray came from a source which lies on this line. If you have just one ray, you cannot tell where the source, but somewhere on this line. Then again, brain will interpret that this ray came from a source which lies somewhere on this line. And of course, exactly the same we can say about this ray. Again, according to our brain, this ray came from a source which lies on this line. And of course, all these 3 lines are going to intersect at one point, and to our brain, that will be the source of these rays, right? And that is the object for our brain, right? But of course, we know that that is an virtual image, right? Which is, of course, you can apply law of reflection, right? And you can easily show that this distance s from the mirror to the object equals to the distance from this image to the mirror, right? So this is a virtual image. And why do we know it's virtual image? Because we're trained, right? We know that that is just a reflection, right? But if our brains were not trained from the very beginning, right, when we were born, right? If our brains were not trained, so most likely we would have fun like cats, right, fighting with their image, with their own images, fighting or having fun, right? Yeah, because their brains are not trained to understand that that is just a reflection, that is just a virtual image of them. Okay, so that's how image formation. That's how we can discuss image formation. All right, in a on a smooth surface in a mirror. Right. Okay, so now let's make a system more complicated. Instead of one point, let's say we have something like a pine tree. So again, so how can we discuss image formation in this case? In exactly the same way like before. We can discuss only 2 points. For example, we can take the top of the tree, point P, and in exactly the same way like we just did, we can come up with a conclusion that the virtual image is going to be at this point, at the same distance from the mirror as an object, as this point from, as the distance from this point to the surface of the mirror. And then we can take the bottom of the tree and get this point Q prime. And of course, between these 2 points, there will be the rest of the tree. Right? So that's why, that's how image are formed. That's how we can discuss image formation, right? That's how we can model image formation in the mirror. So you see, it's quite simple. Ray optics is much simpler than wave optics. So now the question for you, right? After this, again, I created the poll in the chat, so you can use that. So what do we have here? Basically 2 bulbs, right? 2 active sources, which are basically points. Then there is a opaque screen, and there is a vertical hole in that screen. And let's assume that the width of that hole is kind of reasonably big enough so that we're not going to see any diffraction effects, right? So the size of that hole is larger than wavelength of these sources. And then behind this screen, there is a viewing screen. So the question is, what are we going to see on that viewing screen? Option A, 2 dots, right? Option B, 2 horizontal lines of light, 2 vertical lines of light, this complicated picture, or just a rectangular of light, right? Okay, give it a try. The poll is in the chat. You can see it. You should be able to see it. Okay, let me step away. Okay, I see a distribution. Again, I said, guys, so the width of this hole, the width of the hole is much larger than the wavelength of light. Okay, we have a leader. Again, I'm blocking. There's no option other. Somebody managed to find option other. Okay, I will look at that after class. Where did you manage to find it? Okay, guys, it should be enough of time to answer. All right, so let me just quickly discuss. Right, it's a reasonably simple question. We just need to draw, again, as I said, a few rays. Okay, so let's look over here. So let's take, for example, first one bulb, 1 point source. And here's our screen, this screen with a hole. So, and viewing screen over there. So again, I will just draw. Of course, you can draw as many rays as you want, right? So this point source is going to send rays in all possible directions, right? But we just need to look at a few. Usually, as I said, 2, 3 rays are more than enough, right? So let's take 2. Actually 3. The first one, which goes through the top, okay, right, of that hole. Of course, it will end up at that point on the screen, right? Just a straight line, because that's how we model lights, with a straight line. Yeah, the central, we can skip this ray, but anyway, just to have a nicer picture, I also drew this ray which goes through the center of the hole. But basically, we just need to look at this ray and this ray, which goes through the bottom, right? So this ray, of course, is going to end up at that point. And so basically, between this point and that point, we have light. Light will be distributed. So you see this yellowish line. So that's the how to say? I want to say image. No, just a distribution of light. Distribution of light. That's this distribution of light on the screen. So this point source is going to create this vertical line of light. Vertical line of light. And since we have also 2 sources, so behind this source there's another source, point source. Of course, it is going to create another vertical line of light on the screen. So we're going to see something like this. All right. So in order to get, for example, B, what do we have to do in order to get B? So we just need to take this. Okay, let's say take this this screen and turn it by 90 degrees, right? So that the hole would be horizontal. In that case, you will get this option. This is basically diffraction effect. It's possible to see something like this if the width of this hole will be somewhat comparable to the. No, we're not going to see anything like this. Forget about. So, well, how about this situation? So how can we get this a distribution of light on the viewing screen? We can get that if we take, for example, a much larger number of bulbs and position them over here horizontally. For example, next one, then here, another one, another one, another one. So if we, for example, create a, for example, if I take this bulb, basically a bunch of point sources, right? And with this screen, right? With this hole on the screen, right, and this source, yeah, we can get the rectangle. We can get that that distribution of light. Right. So now, so the answer is, of course, C for this question. So now let's move to the refraction. Now again, we just discussed reflection, now refraction. Well, refraction is slightly more complicated, but not much. Again, let me remind you, again, the refraction is, so if you have a 2 medium, for example, here, let's say, here we have air and then glass. So incident ray, sorry, I need to mute. Okay. So we have incident ray, and then this part of that light will be reflected. We just discussed it, and part will be refracted. So it manages to enter the second medium. So let's discuss this refracted ray, and of course relative to the incident ray. So first of all, we need to introduce what is called the index of refraction. When light propagates through medium, of course it propagates differently in different medium. So if a light propagates in a vacuum, of course it propagates with the largest possible speed of light. All right, 3 times 10 to the power of 8. If light propagates in some medium, let's say air, the speed will be slightly slower, right? If light propagates in glass, the speed will be even slower. So basically, in order to describe those optical properties of the medium, so we need to introduce some parameter. Actually, probably, yeah, I should have added transparent medium. So we need to introduce some parameter. Again, which parameter? It's up to researchers, right? So, but researchers actually finally introduced this parameter, which is called the index of refraction, and it is introduced in this way. N equals speed of light in a vacuum, 3 times 10 to the power of 8, divided by the speed of light in this or that particular medium, right? So if it's a glass, for example, so speed of light divided by number which is less than speed of light slightly, right? As a result, this index of refraction, the minimum value of index of refraction is 1, right? So in a vacuum. But if it's a medium, some medium, every time index of refraction is larger than 1. So 1 is the minimum value. N cannot be less than 1. All right. And of course, as I said, N equals to 1 in vacuum. All right, so here I took a table from the book. So you see, in a vacuum, index of refraction 1, and then it starts growing, right? Water 1.33, glass 1.5. Very often books use this number. This medium, water and glass. Okay, so now let's discuss refraction. So let's assume that there are 2 media and the surface is smooth between them. So for example, it can be air over here, right? And maybe glass or water, right? So, but anyway, we can call it medium 1 and medium 2. So, and let's assume that, just for clarity, let's assume that this medium is denser. So index of refraction is larger. Index of refraction of the second medium is larger than the index of refraction in the first medium. And now let's draw our rays. So incident ray. Then, of course, this incident ray, part of this incident light will be reflected. So we know how to describe that. So there will be a reflected ray. And of course, we know how we can define directions using angles. So angle of incidence and angle of reflection. And of course, we know that this angle and that angles are equal to each other because of the law of reflection. So theta 1 and theta 1. Then, but now, of course, there will be also a refracted ray, right? Refracted ray. And so basically, you see direction of incident ray is that. Direction of refracted ray is slightly different. So there is like a small kink over here at the surface. And of course, we can define direction of this ray, refracted ray, using what is called angle of refraction. And again, you see it's between the normal line and the direction of the ray. So now we can call it theta 2 because it's a medium 2. Okay, and so now to describe this refracted ray, we can use Snell's law. Snell's law, right? So which basically connects indices of refraction and these angles, angle of incidence and angle of refraction, right? Most of you are familiar with this law, right? N1 times sine of angle of incidence equals to N2 sine of angle of refraction, right? So Snell's law, and again, it can be derived. Again, as I said, if you write a wave equation for this medium, for that medium, apply a boundary condition, try to match boundary, match some parameters at the boundary, so you can get these automatically just from calculus. And again, at some point, you will do it in the higher level classes. Okay, so now let's play a little bit with this law of reflection, and then law of refraction, Snell's law. And then let me look at the problem. So, a case when N2, so this is a denser medium, for example, a glass, and this is air. N2 is larger than N1, right? So again, angle of incident ray, angle of incidence, refracted ray. Okay, I will open it up later, right? So now let's look at Snell's law in order to understand how should we draw the refracted ray. So N1 sine of angle, sine of theta 1, and 2 times sine of theta 2. Since N2 is larger than N1, it means what? What can we say about the angle theta 2? It must be smaller than angle theta 1, because their product of this and product of that must be equal to each other. If N2, you see, N2 is larger than N1, then it means this factor must be smaller than that factor, right? Because their products are equal. So if N2 is larger than N1, then we can say that theta 2 is smaller than theta 1. Right? So it means that yeah, it means what? It means that angle of refraction is smaller than angle of incidence. So basically, this refracted ray bends towards the normal line. So you see, theta 2 is smaller than theta 1. All right, so ray of refraction or refracted ray bends towards the normal line. In the case when light goes from medium with smaller index of refraction into the medium with larger index of refraction. Okay, so now opposite situation. So what if we have this medium is denser, so index of refraction, you see N1 is larger than N2. And this is, for example, glass, air. So in this case, again, the same ray of incident ray. Right? And so now again, let's look at the Snell's law and analyze in exactly the same way. Since N1 is larger than N2, so N1 is larger than this N2, so it means that this angle must be smaller than that angle, right? So this angle theta 2 is larger than this, so this ray of refracted ray will bends away from the normal line, right? So you see, now theta 2 is larger than theta 1. So it's a simple analysis of Snell's law in order to figure out what happens to the to the ray. So in this case, it bends towards the normal. In that case, it bends away from the normal. Right. So now it looks like after this, it's time for me to look at the problem. Yeah, okay. Now let me switch to whiteboard. We still have 10 minutes. It should be enough to finish discussing the problem. And as I said at the beginning of the lecture, very similar problem will be in your homework. I added to your homework. Oops. So what do we have in this problem? Swimming pool. You see cross section of a swimming pool. We know the width of the swimming pool, 4 meters. All right. So of course it filled with water. Index of refraction we can easily get from the table. So N2 equals 1.33. Here air, of course, right? Index of refraction is 1, close to 1, but we treat it as 1. So then at a particular moment of time, okay, let me remove these magnets. I keep them here so that the screen wouldn't erase the drawing. So let's assume at a particular moment of time in the afternoon, when the sun is 20 degrees above the horizon, right? At that moment, the bottom of the pool becomes completely shaded. At that particular moment of time, the bottom of the pool becomes completely shaded. You see that's what I wrote. And it happens at the moment when the sun is at 20 degrees above the horizon. So we need to find the depth of the pool. Typical situation, you know, sunbathing by the pool, right? And you decided to measure to calculate the depth of the pool, all right? So what can be done? So first of all, we need to draw a nice picture, right? And so at this moment of time, okay, first of all, I drew a few rays, you see, right? And I drew them parallel to each other. Why? Because the sun is so far away. So with an extremely good approximation, they are parallel to each other. So there is no point of treating them as not being parallel. They are parallel to each other, right? And of course, if at that moment of time the bottom of the pool becomes shaded, right? So it means that the last ray, which is going to hit the bottom of the pool will be this ray number 1. After the refraction at this point, it is going to hit that corner. So ray number 1 will be the last one hitting the bottom of the pool. The rest of the rays which are going to hit the surface of water at this point, that point, they're all going to end up on the wall of the pool, right? So of course the wall of the pool will be illuminated still, but the bottom will be completely shaded, right? So that's the situation. And now we need to find the depth. So first I will discuss sort of in general steps which you have to make, and then of course we will go through the details. So first of all, we will have to apply most likely Snell's law to find this angle, right? Once you know that angle, if you look at this triangle, right, it's a right triangle because the pool has a rectangular shape, right? So if you know this angle and you know this side, opposite side, you should be able to find side which is adjacent to the angle, right? So 2 steps. First, you apply Snell's law to find the angle, and then property of a right triangle. Using property of a right triangle, you should be able to find the depth. Okay, so now let's do it. All right, so first, Snell's law. So which is N1 times sine of theta 1 equals to N2 times sine of theta 2. And we need to be careful with angles, because when I solve the problem like this in recitation classes, some students used wrong angles. They just grab the angle, whatever angle is available, right? And quite often it's the sort of wrong approach. Theta 1, you remember angles, these angles. Angles between the normal line and that or this ray. In our case, theta 1, it's this, okay, let me use black. So let me draw this normal line, right? And this is theta 1 between the direction of the ray, number one, and the normal line. So we need to use that angle. So we can write, so theta 1, because it complements angle phi to 90 degrees. So theta 1 equals 90 degrees minus phi. So it will be, of course, 70 degrees. 90 minus 20, 70 degrees. So that's theta 1. Because sometimes students just grab phi, plug it here, but of course it's wrong. In theta 1, of course, on the diagram, it's at that angle. Angle of refraction. Angle of incidence, angle of refraction. Okay, so now we can easily find, basically this is given, this we found, this is given, so we can find theta 2. Piece of cake, right? So let's write theta 2 equals, of course it will be arc sine of n1 divided by n2, n1 divided by n2, and times sine of theta 1, right? So all the numbers are given. So let me look at my notes to find the answer. The angle is 44.95. Okay, I used more sig figs because it's not the final answer, right? But it's almost 45 degrees. Almost 45 degrees. All right, so now the next step, we need to look at this triangle. Right, obviously, let me label this. So this is point A. Let's call this point B, and this point C, right? So now the next step, look at the triangle A, B, C. Right, properties of a right triangle. So I can write that tangent of this angle theta 2, tangent of theta 2 equals, again, you remember tangent, it's a ratio of an opposite side to adjacent. Opposite versus adjacent. So opposite is W, the width of the pool, and the depth which we need to find, this depth. Of course, it's this, BC. Right? So divided by D. So W divided by D. So we need to find D. So D will be equal W divided by tangent of that angle theta 2. Almost done. So W is what, 4 meters divided by tangent of 44.95 degrees, right? So it's almost 45 degrees, right? 45 degrees, so tangent of 45 degrees is 1. So it's, okay, equals 4 meters. So the depth of the pool is 4 meters. So very similar problem I added to the last homework, number 14. I saw that some of you already finished, right? But it shouldn't take much time to solve one additional problem. Right? So there will be some person with a laser pointer trying to find the goggles in the swimming pool. Very, very similar situation, similar geometry, and similar idea to solve the problem. Okay, guys, so that's it for today, and it's basically the end of this semester. It's the last lecture, right? And some of you actually still going to have recitation classes today. But anyway, it's the last lecture. Usually I want to say, okay, thank you for a great semester, but it's so weird, virtual classes, when I don't see your faces at all, right? When we don't have communication normal, right? It's not the best way of teaching. But anyway, so that's what we have for now, and it looks like we're going to have a similar situation in the spring semester, at least for now, I've heard.